Thank you, Albert. The theme for this year's forum is standing on the next frontier of real estate. I kind of think like we're already there. This has been quite a year with lots of buzz about AI and robots and blockchain and 3D printing. It's in the news every day. So the key is to try to make sense of it and understand what it means for the built environment. But to help us to really get a peek about what the future really might look like broadly, one of our colleagues, we're thrilled to have Erik Brynjolfsson here. He's the director of the MIT Initiative on the Digital Economy. You may have also read one of his many co-authored books, Machine Platform Crowd, which just came out, The Second Machine Age, which was outstanding, Race Against the Machine. These are all a tremendous look into what I thought was going to be further away, farther down the road. It's happening sooner than I thought. He's going to tell us a little bit about that. So with that, I'll turn it over to Professor Brynjolfsson. Thank you, Erik.
Thank you, Steve, and thank you, Albert. It is such a delight and an honor to be here. I'm really interested in not only getting a chance to share some of the research we've been doing at the MIT Initiative on the Digital Economy and with my colleagues at Harvard, Carnegie Mellon, and Stanford, but also hearing from all of you, some of your questions and comments. I'm going to leave some time for Q&A. It's my belief that artificial intelligence is going to have profound effects on real estate, because AI is going to have profound effects on our society and our economy. AI also has some very specific applications to real estate in areas of big data, image recognition, and asset pricing, and I'll talk a little bit about those as well. So let me give you a little bit of context first, and there are a lot of things that have changed society, and we read in the history books about kings and queens and societies that are at war, or plagues, or new discoveries. But from an economist's perspective, technology really is the big driver. In fact, if you look at the vast sweep of history here, and you can look at a lot of different metrics like GDP per person, or living standards, life expectancy, what you see is that nothing much changed for most of history for the typical person. The average person kind of was a poor subsistence farmer for most of civilization's time, until the invention of some powerful new technologies, most particularly Watt's steam engine that ignited the Industrial Revolution. And since then, living standards have been taking off. Economists have looked at how technology changes living standards, and Bob Solow here at MIT got a Nobel Prize for showing that it's not working harder or even using more capital that mainly drives our living standards. It's new technologies. And there's one class of technologies that economists have particularly zeroed in on, and those are called general purpose technologies. These are technologies that are not only powerful in and of themselves, but that ignite lots of complementary innovations. The steam engine is certainly an example of that. It could be used initially actually for pumping water out of mines, later for driving factories, for obviously locomotives and steamships. There's a whole set of applications that people came up with for this power source that allowed us to replace our own muscles and animals with mechanical power. Later, electricity and the internal combustion engine were similar general purpose technologies. So these GPTs drive economic growth because they have three main characteristics. First off, they are pervasive. They can be applied to many parts of the economy. Secondly, they're able to be improved over time. And thirdly, they're able to spawn complementary innovations. And artificial intelligence is, I believe, our era's general purpose technology. It is the GPT that is set to have similar wide-scale effects on our economy. It is certainly pervasive. The core capabilities are used in just about every industry. Improved over time, well, that's the essence of AI, especially machine learning, as I'll show later, and able to spawn complementary innovations. These core building blocks of AI can be used whether it's in automobiles or in hiring decisions or in recommendation engines or many other types of applications. In fact, one could argue that of all the GPTs that humans have invented, AI may be the most general of all the GPTs. Demis Hassabis, the founder of a company called Google DeepMind, has said that modestly that their goal is to solve intelligence and then use that to solve all the other problems of the world. So I think that's a cute way of phrasing it, but they're making some progress, and they've applied this very powerful set of tools that they are developing, and many other people at other companies and universities are developing to solve all sorts of different kinds of problems. Now, there were really two big waves of artificial intelligence, and for that matter of computers and software. The first wave of the computer revolution is when we taught machines what we know. That is to say that we codified our knowledge. In fact, the word coding that most of us have at some point done is really codifying knowledge. You figure out what steps you want a computer program to carry out, and then you have to write it very, very precisely. And if you've ever written computer code, you know if you get it a little bit wrong, if you have a comma or a word in the wrong place, it just doesn't work. So you really have to understand what you're doing. And if you understand it well and can codify it, you can write some code to do it. And then once you've codified it, you can digitize it. And once you digitize it, you can replicate it. And that's really the mantra that led to trillions of dollars worth of value in the first wave of computerization. And many, many big companies from SAP and Microsoft and many others were based on this idea of taking some steps in a business process, codifying them, then digitizing and replicating them. The economics of that are that you have relatively high fixed costs. It takes some time and effort to initially figure out how to make a piece of software. But then once you've made it, it costs almost nothing to replicate it. You can make a dozen or 1,000 or 1,000,000 or 1,000,000,000 copies for almost nothing. And that leads often to winner-take-all markets. It also leads to creation of a lot of potential value. So that's great, but there are limits to that. And Michael Polanyi said it well, and the limits are that even though we can do things, we don't always know how to explain them and how to codify them. As Michael Polanyi, the philosopher in the 1960s, said, we know more than we can tell. So there are many tasks, like this is my mom and dad. I can recognize her face and his face very easily. I can easily tell who isn't my mom. But if I were to write down some computer code, it would be very difficult for me. I mean, do I write how many centimeters apart her eyes are, or exactly where her ears are, everything? It would be very hard for me to codify that knowledge, even though I can instantly do it. And all of you can instantly do that as well. And there are many tasks like that, whether it's riding a bicycle or famously the game of Go. Go players, it's a very structured game. There are very simple rules for it. And you'd think you might just write a computer program to step by step describe how it's played. But it's just too complicated. There are too many possible steps. And Go players themselves can't say how they play the game of Go. Instead, they look at the board and the right move just comes to them. They understand what it is. And we know it's the right move because a good Go player will win the Go game. But ironically, if you ask them, how did you win that game? They'll say, I don't know. It just came to me. So we recognize how to do many kinds of tasks. But since we can't describe them, we can't codify them. And that historically has put them off limits to making computer programs for them. Still lots of things we can write computer programs for them, but there's this whole other area of human knowledge that so far has been uncodifiable and uncomputable, therefore. But now we are entering what Andrew McAfee and I call the second wave of the second machine age. And that is a second wave where machines can learn how to figure things out. And it's part of this area of artificial intelligence, getting machines to mimic human intelligence. But this new wave is based on machine learning using large data sets to get machines to do tasks without being explicitly programmed. And there's one category in particular that's been especially effective, and that's this area of deep learning. It's a type of machine learning where you show the machine lots of data, and it uses artificial neurons, loosely based on human neurons, in your brain, to figure out how to solve problems. And people have been tinkering around with this for decades with fairly limited success until about 10 years ago, and then it started really taking off, in part because we had a lot more computer power, so we could make much larger networks, in part because we had a lot more data so we could train them, and in part because there were some improvements in the algorithms themselves, even if the core idea of back propagation, as it's called, was invented over 30 years ago. And as a result, we have now crossed an important threshold. Here's some data from a large data set called ImageNet. Fei-Fei Li at Stanford put together about 14 million images and painstakingly had humans label what each of the images was. So that took some time. So you could label everything that's in these images, but you can now use that as a way to test how good the computers are. And how good are they? Well, they've rapidly improved. The blue line here shows you how back in 2010, there was only about a 70% success rate. Over 25% of the images were mislabeled or not able to be labeled. But then there was this very steep line here around 2011, 2012, where it really started improving a lot. And that's when Jeff Hinton and some of his colleagues started successfully applying deep learning techniques to image recognition. And that proved to be a very effective technique. And now just about all the systems use this approach. And as you can see, it's improved so much that it's now actually surpassed human level. Humans are about 95% accurate. You can't always tell whether that's a lemon or an orange over there. Or the ones that get me, I've looked at these, is they have different species of dog, or different breeds of dog, I should say, different kinds of birds. And I don't always know the names of them, but the machine is able to label them much more accurately now. And it continues to improve. The most recent data is down with about a 2.5% error rate. So it's gotten to be quite good. Now, this is not just for image recognition. In principle, any kind of a system where you have data for inputs and outputs that are labeled, where it's described what is the example, the way those images were labeled, could be a candidate for a machine learning system, especially this category which we call supervised learning systems, where you basically show it what the right answer is, and once it's seen a few examples, it can then extrapolate to other examples. For instance, instead of images, you could do it for voice. And one of the reasons that Google and Siri and Cortana have gotten so much better at recognizing our voices, I now actually dictate most of my emails and texts because it understands them quite well, even recognizing people's names, is because there's been more and more training data. And just as you can recognize an image, you can train it on words, and it can create a transcript out of that and begin to understand it even. You can obviously caption photos. You can figure out which recipes are likely to lead to better reviews. You can figure out what the optimal way of doing traffic flow is. Many of you in your companies probably have applications where you have some sort of labeled data. And I encourage you to think about how you could use that labeled data to create a machine learning system. It doesn't have to be millions of examples. Sometimes you can do it with a few thousand examples. And this is taken from an article I wrote in Harvard Business Review last year that goes into more depth on those kinds of systems. So there are many broad applications. Let me very briefly describe some of those kinds of applications. One set of them is around vision and language. I just showed you an example of each. Another is in interacting with the physical world, like robotics. And a third one is in solving problems. A lot of big companies are using them now to solve all sorts of their internal problems. So let me give you a few more image recognition examples, not just recognizing faces at Facebook or places like that, but you can use it to help diagnose cancer. You can show it lots of medical images, and some of them were from people who ended up surviving, and some of them were for people who didn't end up surviving, and the system can start identifying what are the differences between them. And in fact, there have been papers now published in places like Nature and Science where they have done head-to-head comparisons, and the machines are matching or even surpassing human radiologists and dermatologists at recognizing images. They are finding characteristics of those images that were never taught in medical school because the machines were able to pick up on those images. So this is very promising for improving many kinds of medical diagnosis through this image recognition. Another one is in recognizing real estate. So I picked this one because I thought it might be particularly relevant to this audience. My colleague, Nikhil Naik, I think he's right over there, has been working on a system that was, the precursor of this was published in the PNAS, and there's a set of working papers coming out looking at images of streets from, for instance, you guys may know that Google Street View, as you go to Google Maps, you can see images of all of the buildings on a particular street. Well, guess what? That is training data. You take the images of the data of the buildings, and you match them up to the prices, the price appreciation, which ones have been more successful investments and which haven't been more successful investments, and then you start seeing which patterns are in there. Can it detect things that human real estate appraisers could not detect? And the answer is yes. We can actually outpredict what the humans would have guessed in terms of which homes, which neighborhoods, which buildings are more likely to appreciate and which ones are less likely to appreciate. And so we even have a venture around that called Max Gradient now. Another category is in speech recognition. And here again, you can trace it and show how the machines are beginning to pass the humans in that. The second big group of applications is in interacting with the physical world. Maybe the one you've heard the most about is in mobility. Our colleague Daniela Roos is involved in a company called Nutonomy that does self-driving cars. Of course, there are many, many other ones you've heard about. Tesla, Google's Waymo, or I should say Alphabet's Waymo unit, Tesla, GM, Toyota, BMW, so on and so forth are all working on these self-driving vehicles. Andrew Ng introduced us a system in Frisco, Texas last week called Drive.ai that is shuttling passengers around in self-driving cars where there's no human driver. They still have kind of a chaperone riding in the car just to make sure, but they'll eventually plan to have that person go away as well. This has huge implications for city planning, for real estate prices, for the costs of commutes, for the efficiency of parking and many other things. Likewise, these systems are helping in robotics and allowing factories to run with a lot fewer humans and become much more efficient in that way. I've visited many factories in the United States and China and Europe where fewer and fewer human workers are needed, warehouses, distribution centers as well, and these systems are allowing some big changes in the workforce accordingly. And finally, I'll mention briefly this category of problem solving, answering different kinds of unstructured problems or pattern recognition. For instance, I was giving a talk at JP Morgan about 6 months ago, and they brought together all their top executives, and then they described to me this system, which I read about later, that is using these systems to do what lawyers would have taken 360,000 hours to do. So it's a big replacement. And Jamie Dimon said that one of the things he wanted me to do in speaking to his top executives was convey to them the speed at which some of these applications were going to be hitting his own organization and how they needed to prepare for it and think about ways of redeploying people as some of the previous tasks they've been doing could now be done by software. So this last one underscores a broad point that we make in our book, The Second Machine Age in particular, and some of our other writings, Race Against the Machine, and some of my academic writings. And that is that while digital progress, including artificial intelligence, makes the pie bigger, it allows us to create a lot more value with a lot less effort. So productivity is helped. It doesn't necessarily mean that everyone's going to benefit evenly. There's no economic law that says everyone's going to get a share of that bigger pie. It's possible for some people to be made worse off, not just in relative terms, but even in absolute terms, even as technology improves things. In fact, if you look carefully at the economic theorems, it's possible for a majority of people to be made worse off while the pie grows. How is that possible? Well, that's if a small group of people get huge disproportionate gains, perhaps 1% of the people getting hundreds of percents of gains, and the other 50 or 90 or 99% of the people actually being made worse off. Now, through most of history, that is not what happened. When you looked at the earlier general purpose technologies, the steam engine, electricity, and so forth, there were some winners and losers, the Luddites, people who made, blacksmiths making horseshoes or something that may have been made worse off. But in general, it was a rising tide that lifted almost all boats. Unfortunately, over the past 20 or 30 years, things are a little different. There's been something Andy and I call the Great Decoupling, and it's very disturbing, and it's something we need to pay more attention to. And that is that although productivity, the blue line here, has continued to grow in the United States and around the world, and is now at a record high, median income, the red line, is becoming decoupled. They were closely tied together. More productivity meant that the median person was better off, but now it's lower. How can that be possible? Well, median, as I remind you, is not everybody. Median is the person at the 50th percentile. And the 50th percentile doesn't have to be the same as everybody in the society. If a lot of those gains go to the top 1%, the person at the 50th percentile may not get anything at all. And in fact, recently median income has kind of stagnated. I should extend this. The last few years, starting in about late 2015, it began to tick up a little bit, but it's still below its peak back in 1997. So that suggests that we still have quite a ways to go. And there are a number of reasons for this. It's partly due to some changes in demographics, in globalization, in tax policy. But I believe, and I think most economists would agree with me, that the number one reason has been the ways that technology has affected the economy and the way technology is being used. Larry Katz, who's a labor economist, leading labor economist at Harvard, has said that. Larry Summers, a number of Nobel Prize winners, agree with us that the primary driver of this has been the way that technology has rolled out. Now that's looking backwards, which economists, of course, by nature, if you look at statistics, that's what it's going to be. I've also been involved in a report trying to look forward, what's likely to happen with the new technologies. One of these reports was the AI 100 report that I wrote, where we concluded that the economic effects of AI on cognitive human jobs will be analogous to the effects of automation and robotics in manufacturing jobs. So we thought that the future may look very much like the past, but for more of the economy. As I've thought more about that, I really would amend that. I'm not as sure anymore that going forward, things are going to be the same as in the past. And there's two main reasons for that. Number one, while these technologies are very powerful, we have to remember that they are tools. And you can use tools in many different ways. And one of the things that we humans need to think about is how we want to use these tools and how we want to shape society. And I'd be delighted to talk with you more about that during the Q&A if you're interested. The second reason is that these new technologies are in many ways quite different from the old technologies, not simply more of the same. They're not simply extensions of the first wave. They can do new kinds of tasks. So we shouldn't just automatically assume they will affect the same groups of people, the same types of jobs, the same type of income effects. That's an empirical question that we need to analyze and understand better. So we actually have undertaken a big project to do that, to assess the suitability for machine learning of many different kinds of tasks. The premise of this project is that we are very far from what technologists call AGI. AGI is a broad category of artificial intelligence. AGI stands for Artificial General Intelligence. That is AI that can do all different kinds of tasks that humans can do. AGI is what you see in Hollywood movies. It's what the Terminator has. It's what the machines are that can just outwit humans on every dimension. Let me be extremely clear. We are very, very far from AGI. I don't know that we'll see it in our lifetimes. I don't doubt that it could happen someday, but it's not the challenge that we are facing right now. The AI systems that I've seen at all the top universities, all the top places, and when I talk to all the top technologists, there's universal agreement. We don't have anything close to AGI, and it's not imminent. That said, we do have superhuman AI for certain narrow tasks. Machine learning, as I've already shown you, can do certain kinds of tasks better than humans. Image recognition, getting their voice recognition. Even your calculator, of course, can do arithmetic and math better than humans can. So there's no doubt that in certain narrow tasks, AI is already superhuman, but it's not broadly. Well, that raises an obvious question, which is, so what are those tasks? Are there some characteristics of the tasks where AI is superhuman versus the tasks where humans are still better? And that's really the net essence of this project. Working with Tom Mitchell, who's head of machine learning at Carnegie Mellon, and Daniel Rock, a graduate student here, we developed something we call a rubric, a set of 23 questions to characterize which tasks are suitable for machine learning and which ones aren't. We have a set of, I'll show you some of them later, but basically do you have a lot of data? Is it well specified, and so forth. And then we took these 23 questions and we applied them to a very large data set called ONET. And ONET is something put together by the Department of Labor that characterizes all of the US economy into about 964 occupations. And for each of those occupations, it describes some specific tasks. Altogether, each occupation has about 20 or 30 tasks. So like a bus driver does certain tasks, a radiologist does certain tasks, an economist does certain tasks. And for each of those tasks, we can then apply the rubric and say, is that particular task, is taking change on the bus something that a machine could do? Is driving the bus? Is recognizing stop signs, etc.? And for each of those tasks, we now are able to characterize whether or not machine learning is suitable. We did a first wave of it, crowdsourced it. There are so many tasks that had to be assessed. At first, I did it with a team of undergraduates, and I did some myself. But that wasn't scalable. It was sort of a proof of concept. And so we hired some people through a crowdsourcing outfit called Crowdflower. It's a little bit like Mechanical Turk, if those of you who have worked with them. And we had a whole bunch of people go through these questions. In fact, we had 7 people answer each of the questions, so we get a little bit of reliability testing. And here are some of the kinds of questions that we asked. Like, for instance, is information needed is the information needed in a machine-readable format? And if it is, then that gives you a good chance that you can create a machine learning program for it. So each one of them was scaled on a ranking from 1 to 5. We wrote this up in an article in the journal Science that came out in December, this rubric, and I encourage you to read that. It goes into a little more detail about how you characterize which tasks are suitable for machine learning, which ones aren't. Let me give you a little bit more of an example of what we did. So earlier I talked about looking at medical images. Well, one of the occupations in ONET is, in fact, radiologist. And it turns out radiologists have 27 distinct tasks that they need to do according to ONET. So I didn't know that they had so many different things they had to do. Only one of them, number 4 here, is interpreting images using computer-aided detection or diagnosis system. So that's what I thought radiologists did. And in fact, machines have gotten very good at task number 4. That scored very high on our suitability for machine learning scoring system. But there are many other things, like develop treatment plans for radiology patients, conduct physical exams to inform decisions. These are also things that radiologists are supposed to be able to do. And machine learning hasn't helped with those at all. So as you go through the list of these 27 tasks, what we found was that for radiologists, parts of their job were very suitable for machine learning, and other parts were unaffected. Same thing when we looked at other jobs. For instance, truck driver. Task number 1 is driving trucks. Okay, that stands to reason. And obviously, there's been a lot of progress in self-driving things. But also, they have to wrap and secure goods using pads, packing paper, containers, and straps. They have to check the vehicles. They have to do a bunch of other things. And again, what we found was that machine learning was suitable for some tasks, for not for other tasks. And there's a couple of lessons from these 2 examples. One is that in almost every occupation we looked at, there were some tasks that were suitable for machine learning and other tasks that weren't. So it's a big mistake to just say this job is going to be automated and that job isn't. Instead, it was almost a matter of every job is going to have to change. Your job is going to be affected. Your job is going to change. Parts of it will be affected by machine learning. Parts of it won't. And that means there's a big role for redesign, re-engineering, rethinking work as you reorganize parts of different people's jobs being affected. Rarely does machine learning just run the table. The second thing from these two examples is that one of them is pretty high paid and one of them is not as high paid, but both of them have parts of them that are being affected. This is not necessarily something that only affects, say, low-end clerical workers like the previous wave of technology mostly affected. It affects all sorts of occupations. Now, although I just gave you the caveat that most jobs will have some parts of them that are being affected, it is also true that some occupations have relatively more tasks that are affected in a greater way and others that have most of their tasks less affected. So we went ahead and ranked them. We couldn't resist doing this. So here's what we found. We found that any massage therapists in here? Okay. Because those are the ones that were least affected by machine learning. So their jobs are relatively secure. Concierges, on the other hand, at least according to ONET, have a great deal of their occupations that are replaceable. I guess Google now is working on an automated concierge. So you can look at the different lists, brokerage, clerks, lots of different kinds of clerks. They have a lot of their tasks that can be automated by machine learning. So you can create a scan. I don't see it there. I can't believe I didn't check that. But that would be a good thing for us to look into.
College professors?
Yeah, actually, I did look at economists and college professors. We're almost exactly in the middle of the thing. So sort of half automated and half not so automated. I think that the broader pattern is that even in these tasks, I think there's almost always some part of the job that's not going to be automated. So that's probably the broader takeaway. Another way to look at the data that's kind of fun is through a scatter plot. And what I have here on that horizontal axis, the x-axis, is what the wages are in the US economy. 100 is the occupations with the highest wages. 0 is the one with the lowest wages. And then the vertical axis is how suitable the job overall is for machine learning. The main takeaway I have from this is that it's actually kind of a broad blur. There's not like a big clump down at the low end. Previous technologies were disproportionately affecting lower skilled, less educated workers, and that led to more income inequality. This one is affecting people across the board. That high dot up there, the top left, I think that's the concierges. These are some kind of undertakers. I was surprised that most of what undertakers do is, morticians do is paperwork. They're not digging graves all that much. But you see different kind of a scatter there. It's relatively flat. There's maybe a little bit more at the low end, but it's not nearly as skewed as earlier waves. So that presumption that we had before looking at the data that machine learning would automatically lead to more inequality is not borne out by at least this preliminary data. We're doing some more analyses. We'll understand better as we do more of this. So that said, it will definitely affect asset prices quite significantly, including real estate prices. It's going to create winners and losers, and you can see several ways that affect real estate prices. It's going to affect the kinds of jobs that different cities have. I'll show you in a minute some maps of the US geography, and you can see different parts of the economy have different susceptibility to machine learning. It's going to affect the value of different kinds of property, plant, and equipment as some business processes become more automated and some less so. The value of intellectual property, organizational capital, human capital. And I want to stress that just because machine learning is affecting an industry, that doesn't necessarily mean that industry is going to go away or be automated. In some cases, machine learning may complement what people are doing and make what they're doing more valuable. So you need a more complicated economic model, a more sophisticated economic model. In that science article I showed you earlier, we had the beginnings of a more sophisticated economic model. But for now, the broad lesson is that as machine learning affects a task or an industry, it may substitute and drive down the wages, but it also can complement what people are doing. So for instance, if you can make reading medical images more efficient, there may be more value in having people communicate to the patients what those medical images are. Maybe you'll have twice as many or 10 times as many or 100 times as many medical images analyzed as the machine does it, and now there's a need for somebody to communicate that and interpret that for people. Or as retailing becomes more automated, maybe there's more people who have to pick up and deliver things, even if the long-haul trucks are more automated. So you have to think about a more sophisticated model about what's complemented and what's substituted. And the other thing to bear in mind as we looked at this is that you don't need to have these technologies fully implemented for the asset prices to begin being affected. If investors are forward-looking and anticipate some of the changes that are going to happen in different cities, they will want to make their asset allocation in advance, and you may see asset prices actually precede the physical changes in the economy. But the last point is also an important one. There's a great deal of uncertainty about the timing and the sequence, which parts of it are going to roll out first, so you want to put some error bounds around this. With that caveat, I'll show you a little bit of data about where things are likely to be affected according to our analysis. So here are some of the regions which vary in machine learning exposure. The red ones are the ones that are most affected. The blue ones are the least affected. And it's really interesting scatter plot there. I mean, really interesting geographical pattern there. You can also look at specific categories. So we have a bunch of questions that look at, for instance, image data. So which jobs involve image data, like radiologists? Where are they concentrated? And it's a little different than the general one. We also have separate questions that look at text data. Which jobs have people analyzing a lot of text? And like, for instance, Massachusetts, a lot of people do that, apparently. Parts of Southern California, a lot of the big cities. Which ones have people looking at a lot of speech data, understanding human speech? And in each of these categories, we may have uneven progress in machine learning. It may progress faster in some areas and slower in other areas. And our analysis starts telling you which geographies are more likely to be affected more rapidly. You can also apply this to industries. Different industries have different patterns of tasks. So it turns out that finance insurance is right at the top. And real estate looks like it's number 4 there, real estate and retail investing. So these are some industries that our model says are going to be particularly affected. And a big part of that is because there's already so much digital data in those industries, and that makes it easier to apply machine learning approaches. By and large, they haven't been applied that widely yet. There are some companies like the Bridgewater and Quantopians of the world, Two Sigma, that are using some of these in asset pricing. But particularly in real estate, I think that the industry still has a lot of catching up to do. But our model says there's huge potential for doing it there. And in addition to doing it by geography and by industry, the classic categories, you can create some new categories that we've never seen before. So we did a little bit of algebra to group tasks in new kinds of ways. I won't go through that particular math, but I know that since you come to MIT, you have to see at least one equation, and I think that's a rule. So here's what you get when you apply that equation to the data. And what we've done is we've clumped tasks in different ways. They may or may not be in the same industry or the same geography, but they're related to each other. For instance, these green dots are all clerical workers. Over here, the industrial workers. Analysts, whatever industry they're in, they all clump together. So we've now clumped them in different ways. And we suspect that if a smart entrepreneur or company develops machine learning algorithms that help one of the tasks in one of these clumps, it's probably going to affect all of the tasks there. So these will kind of go as groups or as clumps together. And some of them, like the clerical workers, tend to have a lot of suitability for machine learning according to our model. Others, like industrial construction workers, are relatively less likely to be affected. In fact, here I can show you the high and low machine learning. So our organization, Max Gradient, is trying to use that to predict what's going to happen with asset prices and ultimately what's going to predict which tasks are going to be most affected and how that's going to affect human capital, how it's going to affect asset prices, and including real estate. So I wanted to leave a little bit of time for Q&A and hear what kind of questions and comments you have. Let me just wrap up by showing you the places where you can get more information. As Steve mentioned, I've written a couple of books on this, actually 3 books on this. Our research center, the MIT Initiative on the Digital Economy, looks more closely at how these kinds of technologies are affecting many different kinds of industries. But just about all my working papers, I think all my working papers are available for free at that first URL there, and you can, of course, get the books and articles whenever you'd like to. But let me just wrap up there, and thank you for giving me a chance to share some of the research.
Thank you, Eric. So we have time for a couple of questions. A lot to take in. Just raise your hand, I'll come out.
There's one right in front here.
Hi, I am from San Francisco, and there's a huge wealth disparity right now because of all the technology and growth in the industry. What do you think the long-term impact is on our economy if we continue to see that gap widen because of all this technological advancement?
Well, it worries me quite a bit, and that's one of the reasons I brought it up, is that, it's not just the wealth disparity, but that maps into politics and culture and other areas. And there are people like my colleague Daron Acemoglu who have pointed out how corrosive that can be for a society, for a democracy. We also see that it's spilling over in other areas beyond economics, like deaths from despair. Ann Case is an economist working with her husband Angus Deaton, have described how suicide, opioid, alcoholism, and depression have gone up tremendously, and the death rates, which had been falling for most of the century, have started going up for less educated white males in particular at middle age. Many of the people who have been hit hardest from these earlier waves of technology. So this is something that our society has to worry quite a bit about. I think San Francisco is in the epicenter of a lot of both the creation of tremendous wealth. There are more millionaires and billionaires than ever before, but also a lot of homeless people. Housing prices obviously are extremely high there, and so that leads to a lot of unevenness. I would say that none of that is inevitable, not only because these technologies, as I showed you, in the next wave will affect different types of people than in the last wave, but also because we have a lot of power through our policies, our institutions, what we do in our organizations, what we do as individuals to reshape the income distribution. Income distribution is not something that's sort of decided by artificial intelligence or by machines or by some external force. Income distribution is the interplay of technology and our policies. Other countries have many of the same technologies that we have in the United States, and they have very different levels of income inequality. So to a significant extent, these are choices that we can decide about, as well as things that are affected by technology. So many other questions.
Given what you've told us, what can companies do to prepare? We have immense amounts of data. I don't think we have a lack of data. That used to be the problem. What should companies be doing to prepare for this future, even though it may not be here tomorrow? What can we do now?
Well, a couple things. So specifically on answer to that first question, this is a slide I skipped over, but I'll just bring it up now, is that we'd love to see government policies more to address it, but I think a lot of it has to be done by companies, as you're suggesting. And we have something we call a new grand challenge, the Inclusive Innovation Challenge, which is designed to recognize and reward companies and organizations that are using technology to create more broadly shared prosperity. And we're giving out $1 million to recognize the companies and organizations that are doing that. We're going to have events in Detroit, in Latin America, in Europe, in Africa, in Asia. And then the grand finale will be back here in Cambridge in November. And that will be a chance to see what people are doing in an innovative entrepreneurial way. But more broadly, I think there is a playbook for preparing your own company for the machine learning revolution. And we described some of it in this Harvard Business Review article that I showed you briefly. But it involves understanding the basic technology, particularly this category of supervised learning systems, and looking for data sets that you have that may be suitable for supervised learning systems. Bringing into your company some of the experts that can do this. And the good news is they don't have to be PhDs from MIT that are doing this. There is a lot of good courses that in just a matter of 3 to 6 months you can learn basic machine learning techniques if you understand some basic programming like in Python. And Coursera, MIT, Udacity, Fast AI all teach courses on this that I recommend any of those courses. But the real I think, gap is in people who understand the problem domains that are suitable for machine learning, which I've described a little bit here, but you have to go to my articles to get more depth in that, and the technology, and can bring those together. And hopefully you see the opportunity now. I want to stress that it's not necessary for you to have a big technological company. You don't have to be Google or Microsoft or Facebook to develop these systems. You can use free software like TensorFlow off the web, people who have a bit of training to work on small, simple problems. Let me give you one very concrete, I think incredibly small problem that worked very simply to show you how this can work. There was a farmer in Japan who grew cucumbers. And in Japan, they're very fussy about the size and shape of cucumbers. They have to be graded into about a dozen different categories as to how green they are and how big they are and everything. And his poor mother was tasked with the job of sorting through the cucumbers at the end of each day and putting them into these different bins. Well, he made a simple machine learning system instead that took a camera, looked at them, and after training a few, saying, this is grade A, B, C, D, and so forth, the machine learning system in just about 3 or 4 weeks was able to quite reliably grade them. He did not have previous training in machine learning, used off-the-shelf software, TensorFlow, rigged up a little system, and now his poor mother doesn't have to sort them anymore. But I want to stress that that was something that this is a farmer did on their own. You can read about it in our book. So if he can do it, I'm sure that your organization can set up systems where you have some unique data from your customers, from your hiring, from your internal processes that you could apply for a machine learning application.
And lots of applications in construction.
Yeah, there's many others.
Sure. By the way, we didn't rehearse that. Thank you. Question over here? There was a question back here.
Hi, this is Pulkit Sharma from JP Morgan.
Yes.
So one of the charts you showed had the adoption curve of technology in the different industries, right? So it's interesting that in construction was one of the lowest in that. So
yes.
5,000 years ago, people built pyramids in Egypt with hands and basic tools.
Right.
They do that the same way today as well, almost.
That's right.
But real estate was up there. So real estate and finance were up there, right? Now, for a lot of people sitting in the room, looking at the application of artificial learning of machine learning to real estate. Now, the big challenge there is the lack of data, right? It's not a very data-rich field. So, in terms of the research you've done, what are the low-hanging fruit areas in real estate or at the intersection of real estate investing where it can be applied in the near future?
I think it's one of the best applications. And one of the reasons, I'll be quite frank, one of the reasons I'm speaking here today when I was invited was that I see such opportunity here. And it's because it's going through this transition where there used to not be a lot of data. But if you dig a little bit harder, there's actually a tremendous amount of data that just isn't being used very effectively. And it needs to be brought together. I showed you a little while back the work that Nikhil's doing with Google Images. Google Street View has millions, I don't know, is it billions of images? How many? A few million images from streets. And you can match those up with property records. Likewise, you can look at employment and see employment flows. There are transactions that you can look at. You can look at tax records. You can look credit card transactions. You can look at mobile phone data about where people are, which parking lots they're in and which parking lots they're not in. And if you bring these data together, you start being able to create a picture of what's going on in real estate. So there's an opportunity there. I agree with you, it really hasn't been exploited yet, and so far most people are doing stuff by hand and just doing it from the seat of the pants. So I've met with executives that this is probably one of the ones that has currently the most handcrafted, like a lot of construction still is, but also a lot of data that potentially could be used. And if we bring it together, I think this relatively inefficient market can be made dramatically more efficient, and that's going to bring the spreads a lot closer, and it's going to bring asset prices much more closely aligned. So huge opportunity there.
Hi there.
Yeah.
Kamran Suleiman from John Hancock. We are a life co and we own a lot of office spaces. So
Yes.
one part of the sort of evolution is obviously the number of jobs created and the number of jobs
Yes.
destroyed. But the other side of it is the type of work environment that are going to be more suitable to this new way of thinking and working. So I don't know if in your work or in your colleagues' work, have you looked at what type of working environment is going to
Yeah.
be more suitable to this economy and what type of working environment is going to become obsolete?
I think it's a great question, and I haven't done a lot of in-depth work, but I have a path for answering that question, is that with our model, we can start predicting which kinds of jobs there'll be more of and which there'll be less of. And so I think that even without being, too creative or artistic about what makes for a good work environment, we could look at the types of work environments that people are in for those jobs that are growing and which kinds of work environments people are in those jobs that are shrinking. And my naive prediction would be we'd see more of the former and less of the latter over time. So for instance, a lot of these kind of, these sort of clerical jobs, I think offices designed for them are going to become in less demand. I guess there'll be more, I don't know what kinds of offices these people work in, but it's a little bit different, yeah.
One more question.
Okay, I'll try and be quick. Maybe we can get two in.
Or two more questions.
Okay.
So as we go into, this is Sundar Nagarajan from JLL. As we go into this new artificial intelligence, machine learning, and all of these
Yeah.
technologies coming into play, from what I understand, what is going to be different is we don't no longer look for automation. We got to reimagine,
Yes.
which is very difficult for us to do.
Yes.
I was talking to folks that are in artificial intelligence and particularly in the driverless cars, and they were talking about how the machine doesn't necessarily understand a stop sign. If you put 7 stickers on it, it reads
Right.
it as a 45-mile sign.
Yes.
But the very question I had was, why a stop sign? Are we trying to automate an existing and not necessarily reimagining? How do we get to reimagine?
This is one of the most important fundamental points. I'm glad you brought it up. It might be a good one to end on because there's a tendency, and I did it a bit in my talk for simplicity, to look at the existing tasks and then think, okay, how can we automate that task? And there's a lot of value to be created in that, no question. But the real value comes from inventing new ways of doing business. When electricity was introduced to American factories, at first they simply automated existing tasks and they got relatively few gains. The big gains came when they invented a new way of organizing the factory. And I think we need to, for instance, take automobiles, we need to reinvent the way that cars work. I think that in a relatively short number of years, most people aren't going to want to own a car anymore. Most cars are only used about 5% of the time. But with self-driving cars, you could have an app and the car will come pick you up whenever you want it, wherever it is. And that car could be used 30, 50, 70% of the time instead of 5% of the time as it's picking up other people. Think of the capital efficiency, think of the labor savings, but it's a whole different model. We may want to reinvent street signs and other things as well. But that new system could be 10 times more efficient than what we have today. It won't be if we simply take the existing system and replace the human driver with a robot. That's not the way to do it, and that's going to be true in every part of real estate, every part of the economy. So the challenge that's very hard for me to do on this stage, and it's going to take a million entrepreneurs working in parallel, is to invent new products, new services, new business processes that take advantage of artificial intelligence and not simply think that we're going to take our existing economy and automate little bits of it here and there. So with that closing thought, I challenge you all to reinvent your businesses, your economy, your careers to take advantage of artificial intelligence. And thanks very much for giving me a chance.
Thank you, Eric. So we'll see you at dinner tonight. Yeah, I'm sure there'll be a bunch more questions. Great. Eric, thank you very much. A few housekeeping issues. Breaks and lunch will take place just outside the doors. There's also a breakout room if you need to take a quick break, but you want to keep an eye on what's going on here in the room. And also, please download the conference app, which will give you all of the information, agenda, other attendees. You can reach out to them, other information that we'll be posting there. That's available at the Apple Store and also Google Play. Search MIT World Real Estate Forum. Download that.